Good morning, good afternoon, good evening, depending upon where you are. Thank you all for joining. My name is Sundar Vedantam. I'm in Allentown, Pennsylvania. Today's topic is titled How Hard Is It to Solve? This may sound like a very theoretical lecture, but it does have a lot of implications for both hardware and software design. Particularly, software engineers should know how hard individual problems are to solve, and the algorithms that you implement, what are the impact, the time and space required to run through the program. You should have a good idea, and this understanding, what we are going to discuss today, would help you along in that direction. So I hope you find this useful. The agenda is to talk about problem types. That's the main purpose of this lecture. And as an aid to discuss problem types, we will talk about Turing machine briefly, and then going to talk about P and NP problems. P stands for polynomial and NP stands for non-deterministic polynomial, time solvable problems. And when I have talked about this particular topic, often quantum computing or neural networks, these kinds of computing paradigms come into picture. People ask, since quantum computing works very differently, is it going to shake up this hierarchy of what is possible to compute, etc.? So I wanted to touch upon quantum computing briefly and then show where the hierarchy changes and where it fits in. Then we'll talk about proving NP completeness. That's an important aspect of the theoretical computer science that also shows if you can solve one problem, how easy it is to leverage to solve other problems of similar kind, right? And then we'll do the Q&A in the end, mainly because, as you can understand, each one of this topic can be a semester-long course. This being an overview lecture, we are just rushing through these, and my hope is you will take notes or you would find some of the terminology that we talk about. If it is new to you, you will go look it up later and then find a treasure trove of information that's available online. And of course, most of the other topics you can look up and easily find a lot of good material. Since I've added the quantum computing section in this lecture for the first time here, I was looking through. I wanted to make sure what I'm telling you is all correct. So for the last several weeks, I've been grokking on quantum computing, looking at, actually read entire books to only realize it's not really good. Papers, and then a lot of YouTube videos, articles, and so forth. And there is a lot of confusion. So we need to be watchful on what is it that we are looking at or reading. I will provide a couple of simple YouTube videos that I found that you might find it useful and easy to follow. Right? I keep this legal notice since this has nothing really confidential to Intel, and so I give these lectures outside Intel as well. So this is needed, even though this may not be needed inside. So let's jump into problem types itself. Wanted to start from like the really low end and then build it up to more and more complicated problems. So if you simply take things like adding two numbers or multiplying two numbers, right? The time or the effort needed is actually proportional to the length of the numbers themselves. This is fairly obvious. So in this case, we are adding these two numbers. And so you are going to add 5 plus 5 and then take the carryover and then do this loop and loop all the way around till the end, and then you are done, right? So this is just adding two numbers. Even if you are multiplying a couple of numbers, however big they may be, you go through this process and you have a very clear endpoint. You are done with this particular computation. And the time effort it takes is proportional to how long these numbers are. In addition, it's even simpler. Multiplication maybe a little bit more, but still, if it's a 2-digit number versus 20-digit number, that is what is going to define proportionally how much more time that you are going to take. When I say space, it's actually think of it as the number of bits that you would use up to really do this computation, right? So how much space that you need. That's also kind of proportional to the number. So anything that is of this kind, where it's clearly directly proportional to the number, and if you generalize that number, the number of digits as n, right? And so how big n is, that defines the problem size. The problem size is n, meaning in this case, the number of digits that are there, that defines the problem size. And so if it is some way proportional to n, then it's a very simple, easy problem to do, right? But depending upon what is it that you are doing, the algorithm that you are implementing or the computation that you are doing may require a lot more space and time to complete the computation. So going from a simple addition multiplication, let's go to sorting numbers, right? You all may know bubble sort, in which case, let's say there are 10 numbers, right? And they are in some random order, and then you need to sort them out. And the simplest bubble sort that people have first taught is you start from the bottom, maybe look for the smallest number, right? And if you take the last number as the smallest number and then compare it with the next number, and if the next number is smaller, you take that and forget the previous one, and then go to the next one. If yours is still the smallest, keep that in memory and then go to the next number, right? So you continue all the way up. You are bubbling up the smallest number all the way to the top of the stack. Then you write it there. And then again, you come back, start from the bottom, repeat this routine n number of times because you have n numbers in the stack. And when you complete this n cycle, then you end up getting a perfectly sorted order. I'm sure you all know this. So in this case, you are repeating this n times. And each iteration takes n steps to go to the top. And so the order of this is n squared, right? So if you have 10 numbers, you may take maximum of 10 multiplied by 10, 100 steps to complete this. And this is, of course, as we know in early algorithm class, that's a very inefficient kind of sorting. And this is where improving the order notation, reducing the time and effort it takes to do things becomes more and more important. So then there are merge sort, quick sort, etc. So you all know sorting can be done in like n log n time, meaning n is the size of the number of items that need to be sorted, n multiplied by log n. Within that time, you can do that with like more efficient sorts. And there are always more ideas, versions, implementation going on to see how much can you continue reducing that time, right? It may look like a trivial thing at one point, but if you have millions of records in a database that need to be sorted, etc., what algorithm you use will have a phenomenal impact, right? So that's where this comes in. So when we start talking about this, initially this sounds very abstract. You are talking about, okay, sorting or some multiplying number. So what's the point? And how do you make it really formalized in a very systematic way? How can you think about the amount of effort in time and in space that's required to solve a problem? So to address that question, this Universal Turing Machine, UTM, was introduced almost a century back by Alan Turing. I think it was in about 1936 timeframe. So in this machine, this is a theoretical machine. So you just have a long tape, right? And the tape has squares in it. And you have just one head that can read and write something into just one square at a time, right? And then if you think of this as a digital version, then it can only write 0 or 1, etc. Or it can have write any kind of symbol that you can imagine. And then you write a program saying you read what is written in this one particular square. And then depending upon a table that you look up, the table tells you what to do. Maybe you need to rewrite this cell with something else, and then you move to the left or to the right, right? And then you read what is there, and then based on that, look up your table, and then maybe rewrite something, or you don't write something, and then move to the left or right, and then you just continue, right? That's it. it's like as simple as that, right? So you imagine this tape is of infinite length, and then there is this simple head that does this. Um, Alan Turing showed that with this simple model, you can assess any given problem in the world, and that will tell you how much time it takes, meaning the number of steps this Turing machine needs to keep doing it. So it's not like absolute physical time, but in terms of the number of steps, right? And the space required, meaning how much space you need to complete a computation. So once this is done, of course, this is like a more complicated version of the Turing machine. I shouldn't say complicated. It really shows how it will actually be done. So there is like an eraser. You can read, you can write, and what is there. And then there is this big table. And then depending upon what you find, you move the tape to the left or right, and then you execute whatever you need to. And this has actually been implemented as well, just as a demonstration, right? So there are like physical manifestations of this Turing machine, and this is Alan Turing. If you have heard of Turing test, that's being talked about with in the context of artificial intelligence, again, credit goes to Turing, right? It's the same guy. In fact, in grad school, it took me a little while to figure out Turing machine is different from Turing test. This is like 30 years back. I knew his contribution only from the Turing test point of view, and then I realized how big Turing machine is in theoretical computer science. So he came up with this model, and with this simple idea, we are able to look at any given problem and then figure out how much of time, meaning the number of steps, and the space, the actual amount of space that will be required to compute anything. Once this model is there, we can apply it in so many different ways and then start figuring out the hierarchy of problems, right? So which is more complex, less complex, and which order they all sit amongst each other. So let's consider this simple puzzle. You can do that offline if you haven't looked at that before. So there is an actual number, A, B, C, D, E, meaning it's a 5-digit number. Each alphabet A, B indicates one digit, right? So it's A may be 3, B may be 4, whatever it may be. So it's like a 5-digit number. If you multiply that by 4, you get EDCBA. This number is inverted, right? So it comes the other way. So what's the point of this? This is a problem, right? So you can sort, I mean, you can figure it out. You can write a code to figure out how to solve this problem. In these kinds of problems, the verification of the problem's answer is very easy compared to actually solving the problem, right? So there are these classes of problems where that once a problem is given, how do you go about solving this? Maybe complicated. So even here, how do you go about? I mean, do you start with like each 5-digit number starting with 10,000 and then going all the way till 99,999 and see where it works? Maybe that's not a bright idea. Then, so what should you do? So you need to develop some sort of a solution and then figure it out, right? So brute force may not be the most efficient way. But once somebody tells you, hey, I got the answer, then verifying that is trivial. You just multiply by 4 and see if the answer works out or not. So why are we talking about this? Again, this becomes one kind of problem in the hierarchy of classes, right? So, so keep that in your mind. And then let's look at some other kinds of problems. So we are introducing different kinds of problems. We talked about addition, multiplication. We talked about different kinds of sort. Talked about some puzzles. And then let's look at tiling a surface, meaning you are given a particular tile. Let's say the tile is just this rectangle, right? And then you are asked to come up with an algorithm that will cover this entire room's floor, right? Trivial. So you just put that one next to the other and then you start filling it out. Easy, okay. And then if the question was changed as, forget one room size, can it infinitely continue in all the directions? Again, the answer is trivial. Yeah, just keep attaching it next to each other on the edges perimeter of the current structure, and you can keep extending it to infinity, right? Not a problem. What if the tile structure is more like this? then you start to think, still it's not that big a deal. So you invert this other tile and put it like this. So you more or less get a rectangle, and then you can keep continuing, repeating that structure all along. And so you can do it for a given room or an infinite structure, whatever you want, no big deal. What if the structures are kind of, there is a hexagon, there is a square, there is a triangle? Can you still do it? And maybe you can. So this kind of shows for this particular size, where, for example, the side of the square matches the side of the hexagon, etc. You can construct a solution, and you can keep repeating and so forth. But what if I start putting constraints like, oh, the adjacent colors cannot be the same, or you cannot have XYZ conditions within a given space, etc. Then you need to start developing more and more complicated solutions to get this going, right? So the idea here is, as soon as you start introducing multiple colors and add more restrictions, the combinations of how many, which the ways things can be combined starts to explode, right? And so if you just try to do things by brute force, it may not work in a reasonable amount of time. Maybe it will in infinity, but it's not a good approach, right? So that becomes really important. How well can you solve a problem? Not only that, can you solve a problem eventually? Answer may be yes. Just like taking that 5-digit number, take 10,000 and all the way till 99999, multiply, find the solution. Is that the right way to do? It will give you a solution, but that's not very efficient, right? So that I'm giving like really simple examples to make sense, but if you start digging into it, you will find all kinds of interesting problems. So theoretical computer sciences thought about it, and then eventually there is, I think Turing himself showed that the halting problem, meaning you give a code, you give a program to a Turing machine, and then you're asking a simple question. Hey, will it continue the computation, and at one point will the Turing machine halt, saying I'm done, right? Even that is not decidable, meaning, again, if you simply give one particular program, you can inspect, and then you can immediately, you may be able to say quickly whether the Turing machine will come to a halt or not, right? So the thing may be move 3 steps to the right and stop, or something like that. If that's all it is, you can look at it and tell you. And alternately, if there is a program that simply says while one, right, keep doing it, and you can look at it and say, oh no, it's never going to stop. So these are easy. But the thing is, can you really go into any given program, and can you develop an algorithm? Can you develop a program that will inspect that program to say whether it will end up halting the Turing machine? In that sense, will the computation complete, and then will it come to a stop at some point or not? Even that question is actually undecidable, meaning you cannot create a program that will actually look at any given program to tell you whether it will come to a halt or not, right? So that's called halting problem. Is just the Turing machine, will it come to a halt or not? Decidability is basically, can we decide will the Turing machine halt? So that that it's not possible. You can't write one program that will always decide, right? So you can see the structure building up, and there are more and more complicated problems. And even for some simple yes no answer, you cannot write programs that will completely answer you all the time for all the questions, right? Why is each one of this important? Because in real life, often we may need to solve somewhat of a similar problem. So in this domain, one of the most popular problem is called traveling salesman problem. So it's referred to as TSP. So in this case, you basically have a traveling salesman who has to hit multiple cities in his sales trip, right? And not naturally, he or she wants to cover all the cities by traveling the least amount of distance, right? So if you start from here and then first you go here and then you come back here and then go back here, that may not be very efficient. So you may want to hit the adjacent one first and then go till the end. So again, if the number of cities that he has to hit is only 2, let's say, trivial, right? Go from city A to B and you are done. Even if it's 3, you go from A to B to C, or you go from A to C to B and you are done, right? But once you go to 4, 5, 6, the way in which you can touch all those points continue to explode. So you can see the problem slowly cropping up. So previously, when we talked about the problem size n, taking n square, 2n, 3n, even n cube, n power 1000, whatever it may be, the time and space required at what rate it is racing is still slow. So those are called polynomial time, or like even depending upon how much space it takes, polynomial space problems, right? Whereas here, if you really take the number of cities that one has to travel as n, the combination just explodes. So it becomes something power n, right? And so the n goes to the superscript. And these are exponential space problems, because the amount of time, amount of space that you need starts to increase dramatically very quickly. In our previous ethics and emerging technology lecture, we talked about that 2 power n, the Moore's law doubling every time. We indicated like how big that expansion is, mainly because that's exponential, right? 2 power n, not n power to n square or anything like that. So anytime you put that n on the superscript, it becomes really, really difficult to handle. And TSP is one such problem where this comes into play, right? So when we talk about problems, now the first set is called trackable problem. So there is a very interesting article I wanted to post. Let me give you this link. Hopefully you'll all go back and read this one. Put that in the chat. I will provide this as part of the email, and I send out the recording as well. But if you do get a chance, please go take a look at that. So it is talking about what problems are trackable, right? So this particular article talks about writing code that will keep running a machine for so long and still is the problem trackable at a higher level. Then there are intractable problems, which means it just explodes too much, and beyond a point, you really can't even make out where we are and is it going to be possible to solve this problem or not. And then there is this slightly different other kinds of problems, which are decision problem. So we talked about this halting problem. Given a problem, will the Turing machine stop or not, right? Or the traveling salesman problem can be posted as can the most efficient route complete touching all the cities by not traveling more than 10,000 miles or not? So that becomes a decision problem, right? Or can that be done at 60 miles an hour speed within 3 days? Like, can you touch all the points, right? So those kinds of things. So it can be a decision problem, or it could be an optimization problem. So if you really take the same traveling salesman problem, you don't ask a decidability question. Can it be done within 10,000 miles? Instead of that, we have whatever 17 cities, and how much can you reduce to reach touch all the places, right? Then it becomes an optimization problem. So from a high level, these are kind of the trackable, intractable, decision and optimization problems that we should be aware of. And so once we come to that level of classification, how difficult is it to really solve a given problem can be put together hierarchically this way. So the simplest case is P. P is this polynomial. The polynomial time, polynomial space. Mostly we are concerned about polynomial time item. So if a problem is solvable in polynomial time, that means the problem size n is not on the superscript. It's a number on top of which you put 2, 3, 4, 10, 20,000, whatever it may be. It may sound like, hey, n square compared to n power 1000 is so much bigger. It still doesn't matter. The rate at which it's increasing, it's still polynomial, and so it's kind of doable, more manageable compared to something that is beyond that. So the next level is classified as NP, which is non-deterministic polynomial time. So here is a new notion. So what we are talking about is something like that A, B, C, D, E multiplied by 4 gives you the reverse version. So we said that verifying the solution is much easier than actually solving the problem, right? But imagine in some way you can explore all those paths. You have 10,000 to 99999, so many combination. In a theoretical model, imagine you have one processor for each one of that, right? So you have so many processors running in parallel, each one computes only one kind of thing. In that way, or in some way, you can figure out exploring all those graph paths in parallel and then figuring out which one is the correct one, right? So in that case, again, the time it would take to solve the problem is equal to only one correct travel through that path. I hope what I'm saying makes sense, right? So that is non-deterministic, meaning deterministic is our regular, all the Intel processors, computers running. So you are specifically telling the computer, do this, do this, do this, right? So you are deterministically going through those steps. In a non-deterministic world, in parallel, somehow the solutions will evolve, and then you just need to run through that one case where you get the actual solution. So if it is non-deterministic polynomial time, you need some sort of a non-deterministic computer that will still do that. And this is where some quantum computing notions starts to come in and help, right? And that's why we keep saying things like cryptography, on which all this RSA encryption key, everything that is done may just collapse is because of this notion, and we will talk about that in a few minutes. So non-deterministic polynomial time. Again, non-deterministic meaning running through all the solutions somehow in parallel, and then being able to solve the solution in polynomial time is NP. So beyond that is NP hard. So there is some overlap here, but then it's even beyond that, right? So that's where this hard in the title of the lecture comes from. And in this overlap, there are these problems called NP complete. So this section of selection of problems belong to a specific class, because the traveling salesman is one famous case that belongs to this NP complete class. Because if you are able to solve any one problem in the NP complete class, you can immediately solve all the problems in the NP complete class in polynomial time. Meaning you can reduce one problem to the other. And so if you develop one solution, you can apply that solution to other problems in that class and get solutions for that in a reasonable amount of time, right? So starting from the bottom, so this P comparatively, right? We understand each one. I mean, even if it's multiplication, if I'm giving you 3 digits versus 3 million digits, it's going to take more time. But in the order, this is easy, and then becomes medium. Then there we have difficult, and then the hardest ones are on top, right? So this is how the hierarchy of problems come in. And in that, then there is this containment that we talked about. So the finding a solution, meaning you are given a problem and then you are finding a solution to that problem, that is P. That's like polynomial time. Verifying a given solution, that's why I gave that example of ABCDE multiplied by 4. If you can do only that in polynomial time, but not really explore all the paths one at a time linearly and then get to the solution, then you have this non-deterministic polynomial version. And there are problems beyond that. Even if you have some such magical computer that can do, you still can't solve it in a reasonable amount of time. So the game Go, Go, is famous for that. I mean, the number of solutions, combinations just explode. And so it becomes really complicated. So this containment diagram, Venn diagram sort of thing was developed. Here that BPP stands for bounded error probabilistic polynomial time, because we threw some probabilistic here because we can sort of solve, but it's still not completely 100% error proof, right? You don't need to remember each one of this. I'm just trying to introduce the notion of different levels of problems. So CFL is context-free languages. We talked about P, NP, etc. So there are all these classes of problems. And so if you are able to recognize some problem as belonging to some class, then later on we'll talk about, you immediately conclude that you cannot develop a simple solution, write a code, and then run it in your computer to solve it. And so we need to switch to other kind of heuristic solutions to solve such problems, right? And this brings us to this P and then NP that we saw in the previous case. We said P is polynomial time and NP is non-deterministic polynomial time. Till now, we are not 100% sure if these two spaces are exactly equal. Meaning, is there some intelligent solution, brilliant one somebody can invent? And so similar to that NP complete problem that I was talking about, once you have solution for one, can you make that solution work for all the problems? We don't know, right? And this we don't know status has been in existence for decades now. So whether P is equal to NP question mark is it's called one of the millennium problems in the Clay Math Institute. If we can solve it and show clear proof that it is indeed equal, or even if it's indeed not equal, there is $1 million waiting for us, right? So it's been pretty tough to prove one way or another. Which brings us to quantum computing. Again, we can talk about this alone for a semester, but I'm just touching upon the major concepts. So, compared to traditional computing, how quantum computing works a little bit differently. And as a result, some problems can be solved more efficiently, but we still do not blow up that entire containment map and say, hey, once we have quantum computers working, all this can be solved. That's not the case, right? So the major notions that we need to keep in your mind when you think about quantum computing. First one is this qubits. You might have heard about it. So in our standard digital computers, we have bits, right? So the bits can be 0 or 1. And if you have 3 bits, the status of this bit, the value of this bit, whether it's 0 or 1, has nothing to do with the next one, right? So this can be 0, 0, 0, 1, 1, 1, whatever value in between. So the value of the bits are totally independent. Whereas in quantum computers, the rough equivalent of bits is qubit, quantum bit. And what defines quantum bit itself, there are all kinds of approaches to quantum computing. The most common one that you would see is like a spin of an electron. So it spins one way, it's considered 0, then spins the other way, it is 1, right? And as you know, if you really go at that quantum level, it's not even exactly a spin, it's more like a wavy thing that's going on, etc. But just for this discussion, think of qubits as equivalent to bits in our regular traditional computing, right? And when you have this 0 and 1, which is in terms of the spin, again, if you go in the color, the field strength, anything can be used. You just need two different values that can be applied to a particular state in quantum level. That's all it is. So the easiest thing to think about is spin, and that's what you will see in most of the literature. So in bits, we said it can either be 0 or 1. So you have it written somewhere, if the transistor is on or off. So you always have like clear 0 or 1. Whereas in quantum computing, it's not a clear 0 or 1. And that's where this notion of superposition comes in, meaning it can be kind of simultaneously be in both states, 0 and 1. Then it really depends on your measurement. At the time of measurement, when you are really going in and looking at it, think of this as you are looking at a particular circuit, a transistor, whether it is in conducting state or non-conducting state. It's very clear. It's either 0 or 1, depending upon what charge you apply. Or even if it's something written in the memory, 0 or 1 is very clear, and it can't be both. But in quantum computing, it is both, but only when you are not measuring the value of it, right? Anytime you measure it, it actually it collapses into either a 0 or 1. So when you are measuring, it always similar to digital computer just gives you a 0 or 1. And how it is going to turn into a 0 or 1 depends on some probability, right? So if it's like 85%, it's spinning this way, etc. So when you measure, maybe it will turn out to be 0. But maybe if it was spinning, the percentage is the other way, then it turns out to be 1, right? Again, it may start to sound confusing, but the idea is qubit equal to bit. And instead of it being always 0 or 1, think it can be both. But by the time you measure, it becomes clearly 0 or 1. And the idea is the algorithms that we develop to make use of quantum computing need to nudge this status of all these qubits into the right value. And that's where our intelligence in implementing the algorithm comes in. So that finally, when you measure, the answer you get is the exact answer that you are looking for. And because of this nature, this is equivalent to, I mean, it's not 0 or 1, it's everywhere, but somehow you are nudging it. So you can think of it, you writing a code that is A, B, C, D, E multiplied by 4 gives you EDCBA for that thing. You are in parallel exploring all the combination of that's possible from 10,000 to 99,999. So that is kind of encrypted or encoded in this superposition situation. And the algorithm that you are developing is somehow going to push the computation. So by the time you measure the solution, you just did it in one stroke, right? So it just took like 5 steps to figure out what the actual number is. So that this is what makes this non-deterministic polynomial thing to be done in reality using quantum computing, right? We can come back and maybe another time we'll give a lecture simply on quantum computing, but just want to introduce these main ideas as to why, how it differs with respect to computing. So again, we talked about just one electron, one thing that is spinning up or down, 0 or 1. But in quantum computing, you can take multiple of these qubits and then tie them together, right? So entanglement is basically tying them together. You can do that physically. And when you do this, instead of for you to define the state of where you are, so let's say these are 2 qubits. If it's an equivalent of the regular digital bit, you will simply say it's either 0, 0 or 1, 1. That's it, right? So you can't do anything more. But here, for you to define these 2 bits together, you need to define the probability of each one of these qubits to give a complete sense. You can't just say it's 0, 1. It's not that. It's a probability of the first qubit and the probability of the second qubit. So when you add these two together, that's where that exponential nature of this quantum computing comes in. So it's no longer 2, it becomes 2 power n, n being the number of bits that you have, right? So if you have 2 bits, you have 2, and then you become 3, 4, it basically becomes like 2 power n. So in the normal digital computer, you will have only n bits, but here you are able to encode 2 power n states by adding the probability for each one of these together. In one 5-minute discussion, this may not be very obvious, but I hope just giving you some sense of what it is. And so the next notion to remember is this interference. So this is usually described as, think of you throwing a stone into a pond, and then it creates a set of waves, and then you throw another stone on the other side, then there are two sets of waves that come and cut each other. And when it does, in some places, they are going to cancel each other out. So they have this destructive interference. And then in some places, it's going to be constructive interference, amplifying the total wave amplitude, right? So this notion comes into the quantum computing idea. So you can see how this is represented. So you have maybe a stone thrown here, stone thrown here, and this is creating a bunch of waves, and this is creating a bunch of waves. And depending upon how they are interacting with us, in some places it may be low, in some places it may be more, it's higher than just the wave that would have been created by just one. Again, the idea here is to basically develop algorithms that will help you cancel out all the answers that you don't want by creating this destructive interference, and then amplifying the solution that you want by doing constructive interference, right? So I just have like a 1-minute video, or like less than 1-minute video, where Brian Greene and an MIT prof, they were talking about this particular notion. So let me just show this to you. The whole lecture is some 45 minutes, but it's probably worth listening to if you have time, right? So let me just play this.
To take that symphony and have those various waves, interfere, as you said in the double slit, they're interfering in a very particular way, picking out various locations where the particle could land. But, just sort of visually, in the quantum computer, if you had all these possible outcomes of your many qubits, you'd want to somehow choose those waves to interfere and begin to suppress most of the answers that you don't care about because they're not the answer of interest, and bring to the fore the few or maybe the one answer that you were actually looking for.
Nice graphic.
Like that, huh?
Yeah, exactly. That was well put. Exactly. Yeah, you've got to make, you have to make all these different possibilities, but they're possibilities that exist simultaneously in a quantum mechanical fashion. You've got to make them add up to give you the answer to your problem, and that's tough to do.
And
okay, I'll just stop on that one. Just wanted to show you that it's a nice lecture if you have time to go back and listen to it. So just to summarize, what are the main things that we talked about so that you keep this together in your mind as you listen? So the first one is you should remember qubits. So bits in digital computing, the traditional computing becomes quantum bits, which is roughly equivalent. And then superposition. The main strength of quantum computing comes in because any given qubit can be in multiple states at the same time, right? So that's a range or a spectrum of states in which a qubit can exist. And then entanglement, where you can physically take more than one qubit and then tie them all together. So their total status becomes not just one, but a combination of the probabilities of all of them together. And these two are the ones bringing in this non-deterministic style of computing into quantum computing, right? And then this interference, which is basically, remember the waves, and then we need to design algorithms that will slowly make sure that destructive interference come in, that eliminates all the answers that are incorrect or what we are not interested in, and then amplify the ones that we are interested in, right? And then you do the measurement. So when you do the measurement, of course, the wave function of all this collapses. You just get a clear, simple reading similar to what we get in our traditional computing. But these in-between pieces, right, the superposition, entanglement, and interference, sort of allows you to do this computation in a non-deterministic style. It's not that you are actually going through exploring each one of this avenue one at a time, but you are somehow simultaneously exploring all the options, and then you are pulling out just that one answer that's the correct one in the end. If it sounds like, hey, can you really do this? This all sounds nice, but in reality, does it really work? Yes, it does. That's the most beautiful thing about quantum computing. So even though we really don't have big quantum computing machines, I mean, that can solve like major real world problems yet, there are smaller versions where simple ideas are being tested at this point. And there are more things to talk about. For example, even in that quantum computer picture that I showed, you see it's always like so cooled down, right? Extremely cold temperature. Why is that? That's because anything that goes on around starts adding interference to the quantum computer. So one way to like keep it calm, keep the coherence is the actual term that is used to eliminate any decoherence occurring, is to cool it down so that you can control it better, right? So that's one model that is used. That's what Intel is doing, IBM is doing. I can go look that up. Peter Shor is one brilliant guy in the 1994 kind of time frame. He came up with an algorithm called Shor algorithm that is used in factorization. So that is what started like freaking people out, saying that's a workable, clearly proven, proper factorization algorithm. And like I said, it can sort of work in a non-deterministic polynomial time way. So what we thought would take million years to crack one of the RSA code, if you use Shor algorithm and if you have a big enough deterministic, quantum computer, you can solve it in polynomial time, which means all the encryption keys will become useless, right? So they can be hacked and you can figure things out. So that's a proven working, theoretically workable solution that we already have. And beyond that, now there are like Grover algorithm, which is used in search. And then there are variational quantum eigensolver and quantum unconstrained binary optimization. Can go read up about all these. These are actual algorithms that are being developed. They can be used in like chemical simulations, things like that. So we do have already existing algorithms that are ready to be used on quantum computer at this point. Only problem is we still don't have real quantum computers that are big enough to take this and solve real world problems, right? That is still further away. But now that we have the notion, we are able to do it, then what happens to all this hierarchy that we talked about, right? Then it becomes like this. So basically, it doesn't totally collapse. The NP complete problems are still there. What quantum computer can solve are this BQP. This is B again stands for bounded error. In the previous one, we said probabilistic. Here it's quantum, right? So BPP is bounded error probabilistic polynomial time becomes bounded error quantum polynomial time. So bunch of problems that were not easily solvable becomes solvable in quantum computer. But the main thing to remember is the hierarchy is not just vanishing immediately. So whether you use neural network, whether you use artificial intelligence, machine learning, any quantum computer, whatever BizTech technology that we can come up with, still the hierarchy exists, right? Which is the beauty of this whole field and the reason that we should pay attention to this, right? So this is just maybe waxing eloquent a little bit, but the idea is if P is equal to NP, then the structure becomes more like this, right? P becomes equal to NP, and that also becomes equal to NP complete. So in this case, it also means like everyone who could appreciate a symphony, meaning that is like verifying the problem solution is correct, would be Mozart, because you are it becomes NP. I mean, P equals NP, and so you are able to create equally well. Everyone who could recognize a good investment strategy will also make tons of money, like Warren Buffett, right? So Scott Aronson is the person who gave this nice quote for a world where P is equal to NP. But if it is not equal to NP, then it's it's a world of mystery, difficulty, and frustration. But looks like this is kind of where we are living right now, because we haven't shown that these are equal. So currently it looks like these are separate, but this is definitely not proven at this point, right? So now that we have understood how these things work, so now there are a lot of problems that have been already classified and then put in different bins, right? So if it's like linear search, meaning you have a bunch of things, you're doing a database search looking for something, maybe it takes about n. Then binary search, meaning you cut something into half, right? So let's say there is like sorted number, and then you are looking for some number. If you know if it's more than that, then you can cut that into half and look either it's in the lower half or upper half, right? And then again cut that into half in the upper quartile or the lower quartile, etc. So that is log n time. Then there is insertion start, merge start, matrix multiplication, etc. So these are all polynomial time because the n is at the base, not at the top, right? And then there are a lot of problems that are exponential time. So knapsack, son of subsets, blah, 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 all this, including traveling salesman. So this is all 2 power n, meaning it's exponential time solutions. The idea, as we said, in NP completeness is that the problem that is in NP is also NP complete if and only if every other problem in NP can be quickly, the quickly is defined as in polynomial time, transformed into X, right? What this means is if traveling salesman problem is an NP complete problem, every other, if you solve that problem in a given amount of time, and every other problem in NP can also be solved using the same algorithm in polynomial time. It won't take more time than that, right? I hope what I'm saying makes sense. And this starts to create this kind of graph. So SAT is satisfiability problem, and then there is 3SAT and vertex cover, etc. And then you can see this traveling salesman problem also sitting in this hierarchy. And and this is all not like God-given, somebody else has done, and there is nothing more to be done. Even in my own grad school work, I could show that bandwidth allocation problem, meaning you have a fiber, you have some amount of capacity that's available, and then you have different pieces of like network bandwidth requirement that need to be accommodated, right? So I could show that bandwidth allocation problem is NP complete. And so if you can solve traveling salesman problem, then bandwidth allocation problem can also be solved. So I could get a paper out of that, right? So you can look at new problems that you are looking at and then come up with this notion, show that what is and what is not, and how can something be computed and calculated. So what's the point of talking about all this, right? The idea is if something is decidably very hard, let's say it's an NP complete problem, then you understand that, hey, you cannot do an exhaustive search. You cannot come up with even a super efficient quantum computing algorithm. It's still not going to be completely solved in a reasonable amount of time, right? Then you need to dive into alternate options like neural networks, simulated annealing, ant colony approach, genetic algorithms. So these are all heuristics algorithms that you can apply to solve these kinds of problems, right? So what do we mean by each one? Neural networks, ML, AI, everybody talks about this, so you may know. Simulated annealing, we'll talk about that in the next couple of slides. And then ant colony approach and genetic algorithm are similar heuristic approaches that will give you a solution, but there is no guarantee that it is the correct, most optimal solution for that particular problem, right? Which is probably better than no solution at all. And if you do want an exactly correct, perfect, optimal solution, now we know you cannot get to it for any given problem size. Again, we should keep in mind that if the problem is really, really small, there may be solutions, right? So even traveling salesman problem, 3, 4, 5, 6, even when you are doing vacation travel, you might have figured out, hey, I want to go here first, there first, etc. So it's possible to solve it for smaller problem sizes. The idea is, can you develop a solution that will work for any given size? And that's what we have been talking for the last hour, saying it's not possible, right? So then you need to go into one of these heuristic approaches, which will give you a solution. Maybe it's reasonably good. It could be optimal, but you can never prove it. And so what are the heuristic solution? Simulated annealing. This comes from the idea that when you really heat iron, right, and then you cool it down, and it becomes pliable, right? You can shape it however you want, and as it cools down more and more and more, it becomes harder and harder, and then the shape sets in place. You cannot change it anymore. So the idea here is to start at some random point. So if it's a traveling salesman solution, just pick at random some path that you would choose, right? And then you start tweaking, change this, change that, and see. Let's say you are trying to optimize the total distance travel should be as small as possible. And instead of going from A to B to C, if you go to A to C and then come to B, does the total length reduce? If it is a yes, maybe keep that. And then go to the next step and see if you can continue changing something else from P to Q. Instead of that, go to P to R and then come to Q. Does it reduce the total travel distance? Yes, keep it. No, throw it away, right? So you can keep doing it. But the problem is often it may end you up in some, in an ideal case, you start from there and then you slowly come through these star locations, find your path all the way down to the lowest point, which is the most optimal solution. But in reality, it doesn't work like that. You may be here and then you do a couple of jumps and then you come here. But then when you try to change any the direction from one city to another, it looks like you're always going up. The total distance keeps going up, right? So you would think, oh, I can't take this, I can't take this. And so you get stuck in this, what's called the local minima. And that's not the global minima. You can't get to this point. So in simulated annealing, what we do is in the initial part of the solution development, even if it is slightly increasing the total length, basically it looks like you are becoming suboptimal a little bit, you allow it with some probability, right? So when it is really at the initial stages, you will allow a lot of probability to like jump around, go here and there. And as the solution progresses more and more and more, you start narrowing down that probability. So you are not allowing the solution to make any changes. Again, it's simple to think in terms of the traveling salesman problem. If you want to change from the travel from K to L, you are changing it to K to P, right? And initially, if it's results in increment in the total distance, you still allow it. But as things progress, you keep narrowing it down more and more, so you do not allow it. So the idea is initially you will jump all around, and then slowly, eventually, as the simulated annealing, meaning the temperature cools down, you will kind of come down to the lowermost point. But you can imagine, again, there is no guarantee, right? You may still end up with maybe somewhere here instead of here, which is the ideal solution, right? And similarly, there are other heuristics approach. We'll just talk about a couple and then wrap up. So one is called ant colony optimization. So in this case, think of this as the traveling salesman problem, right? So D, Y, Z, X, S, they are all destination that we want to places that are there. But we really want to find the source to destination. What is the shortest path that you can take? The different kind of traveling salesman problem, meaning you're not trying to touch all the points, but you want to get there as quickly as possible. And if you've noticed, ants, they have this notion of like their ant hill may be at one point, food may be at some other point. Initially, they'll just wander all around and get to the food, right? But once they get to the food, they'll come back, and as they come back, they leave their pheromone trails, right? And then the other ant starts following that, and slowly they can converge, and pretty quickly you'll see they are traveling in the most optimal, efficient path that's possible. So initially, when you start from here, you may be going to X and Y to D. So it leaves a pheromone trail. Then ants keeps looking around. So there are additional nodes found, Z, and then you find this shortest path, and eventually they'll just start doing this. So basically, we are mimicking this happening in nature in the algorithm, similar to simulated annealing. You find a way to basically lay a pheromone trail and then basically explore all the available paths to find the shortest or the best solution that's available for your problem, right? So that's the ant colony approach. So since we talked about these, this is kind of the last slide. So I wanted to summarize and say what do you do when you know that there's no clear optimal solution for a given problem. But before that, since we kept talking about the traveling salesman problem, I found one nice video that shows this in visually, right? Notice how the music also keeps ramping up. We play it from the beginning again. Hope that made sense and captured what I was talking about visually quickly, right? So what is it that we are summarizing? So now we know from a simple addition to all the way up to traveling salesman and beyond, there are problems that can be hierarchically stacked. And then we need to figure out, given a problem, which category does it belong to, right? And if it's a polynomial time solvable problem, okay, that's good. So you can get faster and faster processors, use Moore's law and so forth to just improve the solution so you can get the answer in a reasonable amount of time. But if it's beyond that, if it's NP-complete, etc., doing an exhaustive search won't work, irrespective of what kind of a computer that you have. So then you do need to go into one of the heuristics method. And there are tons of heuristics methods that are available. So depending upon what is it that you are trying to do, you can pick the one that suits your problem, right? That completes the lecture. So I can stop here and try to answer any questions that you may have. Let me stop sharing, close the slides.
Sundar, some very basic question. I'm Shrikant here.
Hi, Shrikant.
We mentioned about the NP-hard problem and in general, the traveling salesman problem and so on. Now, all this starts off with the polynomial and the compute power or the equation to find out the polynomial. Okay. Given a problem statement, how do we arrive at such a polynomial?
I would say, I mean, for any given problem, there is no one simple solution or anything, right? So if it's a traveling salesman problem, you would probably start with, hey, I don't know from where to go. So maybe I'm going to just start settling over and over and over till I finish all the solutions. So maybe that's a starting point for that. So the time it would take for you to figure that out, that's the equation that you are looking for. That is hopefully that's a polynomial solution, but that's what you are starting with. So I would give maybe another example. If it's a multiplication of two numbers, one way to do that is to actually like do the multiplication one digit at a time, or maybe you want to do a log table. So those are all different approaches that you can take to complete the task, right? For each one of that, you can compute how much time and space it's going to require. So that's the starting point. I mean, to answer your question, that's where you start, come up with a solution. And then once you know the steps involved in reaching that one particular solution, then you can come up with how much time and space it's going to require, right? Hopefully it's polynomial, but often it may not be. And if it's not, then you start coming up with alternate solution to see if you can start cutting it down. That's why I was giving that example of sorting numbers. So you start with bubble start, which is n square. Then you realize, hey, I can do better. And then you do quick start or merge start, and you start bringing it down from n square to n log n. Am I making sense?
As a follow-up, Sundar, there's one more fundamental problem with all these computer-based optimization, because it all depends on the random seed from where you are starting. If you take a heuristic approach like a particle swarm optimization, then it depends on where you start. You might hit a local minima and kind of get stuck there. And every time you do, you get different answers. So it becomes very tricky to actually figure out which is the best.
Absolutely. Yeah. No question, no debate there. I mean, since it's like we are throwing up our hand saying, hey, it's an NP-complete problem. I cannot give you a clean algorithm that will run in polynomial time to solve it. Okay, so what's the next best you have? Those are heuristics. Certainly, as we kept pointing out, you may hit some local minima. You may never get to the global minima. So it depends on so many factors, right from random seed to just the chance, right? So yeah, it's there's no clear answer. If there is one, then it's no longer an NP-complete problem, right?
Thank you, Sundar.
Thank you. Yep. Anyone else? Any other questions? Okay. If not,
hey Sundar.
Yeah.
Hey, about this N and about this P not equal to NP or equal to NP issue, right? I mean, you're saying that somebody is still trying to prove, I mean, whether a P is equal to NP or P is not equal to NP.
Yeah.
But isn't that we know that most of us, not Mozart, most of us are not Warren Buffett. Is that basically prove that NP is not equal to NP?
Again, we are talking about theoretical proof. If I need to make a bet, maybe I will say the empirical evidence kind of points us or tips the hat towards P not equal to NP, but it's not been clearly proven yet, right? So it's still an open problem.
But that's what I mean. I mean, mathematically, I mean, to prove something is not correct. You just have this one example, right? I mean, to prove something is equal to something, it's very hard. But to prove something is not true is really, it's easier. But basically, you find the case that is not true, then it means that statement is not true.
You are right. You are quite right. Yeah. But even that's not been done, right? So that's why it still remains a clay millennium problem. It's been an open thing for decades now. We haven't found a way to sort it out.
Okay, thanks.
Okay. Hey, thank you both. Hey, I thank all there are still like 77 people on the call. So thank you all for your time. I hope you found that useful. Thank you all. Really appreciate your time. Bye-bye.
Sundar, thanks.
Yeah, thanks, Sundar.
Thank you.
Awesome.
Thank you, Sundar.
Thank you.
Information about lecturing and how to get more connected with academics and your journey with academics, that would really help many of us to pick up that path.
Absolutely, Srikanth. We'll certainly keep in touch. If anybody is interested in anything like how do you become an adjunct prof, or how do you put together slides, I mean, I'm not saying I'm the greatest guy in the world, but whatever I can think of and I can help you, would be more than happy to. Thank you. Thank you again. Bye-bye.
Thank you. Thank you so much.
Thank you.